So we are talking about the root poset. I'll remind you that the root poset goes as follows. We defined the depth of a root beta to be the minimum length of an element W such that W beta is negative for beta positive. So we have this notion of depth, and then we define the root poset by saying that we have a covering relation between beta and gamma when gamma can be written as a simple reflection acting on beta, and the depth of gamma equals the depth of beta plus 1. And we said that for each one of these edges, the choice of Si is unique, and so we would like to label this edge with that generator Si. Okay. Maybe another thing that I'll remind you is that this depth, remember we said wasn't a mysterious thing. It was basically just half the length of the corresponding reflection T sub beta plus 1. Okay. So these are the covering relations of the poset. Okay. So what I would like to do now is first let me remind you that we talked about the root poset of S4 last time, and we said that it looks like this. And we said that if these were alpha 1, alpha 2, and alpha 3, then this is alpha 1 plus alpha 2, alpha 2 plus alpha 3, and the sum of the three of them. And the only reason I'm repeating this for you is that I want to label these a little bit differently. Let me just label it like this. So this is, I'm just going to label them by the linear combination of simple roots. So this is alpha 1 plus 0, alpha 2 plus 0, alpha 3. This is alpha 2. This is alpha 3. Then alpha 1 plus alpha 2, I denoted like 1, 1, 0. So I'm just writing the coordinates in the basis of the alphas. This is 0, 1, 1. And then 1, 1, 1. So this is the root poset. Okay? And what I want to do now is talk about an infinite root poset, because I told you that in some sense this is, remember that we're in the middle of, or we're working towards proving what I said was the automaticity of a Coxeter group, and I told you that that's a fairly simple thing for finite groups, and it's really more exciting for infinite groups. And so we should do this for an infinite group. And an infinite group that is interesting that we know is this A2 affine, which is corresponding to this Coxeter diagram. Okay. So here the inner product. Here the roots are generated by alpha 1, alpha 2, and alpha 3, and the inner product goes like this. Alpha I and alpha I is equal to 1, and alpha I and alpha j is minus 1/2. That's what this looks like. And And so let's figure out what this poset looks like. So here's the root poset of A2 bar. So we said that the bottom things are the things of depth 1. And so here we have 3 simple roots. Those are going to be the 3 bottom elements of the poset. 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay? And now to get the other ones, we're basically going to start letting the group act on these things. And so, for example, how does S1 act? What does it do to these things? Well, we know what it does to alpha 1. It just sends it to negative alpha 1. And this is negative, so that means that this is not going to be found in the root poset. Okay. What is S1 alpha 2? Well, it's basically alpha 2 minus 2 times the inner product. Well, let me write it down. Minus 2 times the inner product of alpha 1 and alpha 2 times alpha 1. This is minus a half. So what we get is alpha 1 plus alpha 2. Okay? And this is positive, and so this should be above this guy right here. Alpha 1 plus alpha 2. Okay? And maybe I should start labeling these things in colors already. So this is when I acted on S1. Okay? By symmetry, when we do this with alpha 3, we're going to get alpha 1 plus alpha 3. So here's alpha 1 plus alpha 3, and S1 sends me from here to here. Okay? S1 alpha 2, thank you. So this should go here. Again, there's a lot of symmetry here. So for example, what does S2 do to alpha 1? Well, it's going to send me over here also. So let's let S2 be the green one. S2 of alpha 1 is alpha 1 plus alpha 2. S2 of alpha 2 is minus alpha 2. And S2 of alpha 3 is going to be alpha 2 plus alpha 3, which is going to appear here. Okay? And then we go ahead and do this for S3. S3 of alpha 1 is going to send me to alpha 1 plus alpha 3. S3 of alpha 2 is going to send me to alpha 2 plus alpha 3. And S3 of alpha 3 is going to make me negative. Okay? So that's that. How about the next step? We have to keep doing this. So for example, what does S1 do to this guy? To alpha 1 plus alpha 2. You see, I don't even have to compute, right? Because if S1 sent me here, then S1 is going to send me back, because S1 is an involution. So S1 goes down here. What is S2 going to do? Well, it's going to send me down here. And so the only thing that I should be computing is what S3 does. Okay. So what does S3 do to alpha 1 plus alpha 2? Well, we know that S3 of alpha 1 is alpha 1 plus alpha 3. And S3 of alpha 2 is alpha 2 plus alpha 3. So this has coordinates 1, 1, 2. Okay. So I get a 1, 1, 2. And S3 sends me here. Okay. And again, by symmetry, this is exactly what's going to happen here and here. So here's 1, 2, 1. And here is 2, 1, 1. And this should be S1 acting here. And this should be S2 acting here. Okay. What's going to happen here? Well, S3 sends me down. S1 and S2 are going to send me up. And go ahead and compute it, and I'll tell you what you get. You get 1, 2, 2, and 2, 1, 2. And which is which? This should be S2. Should be S2. And this should be S1. By the way, what's an easy way of figuring out what's the color of the edge? Well, you just have to see which coordinate changed, because you know that every time only one coordinate changes, and it's exactly the one that corresponds to the reflection. So that's why I knew that this was S2 and this was S1. Okay. And I can keep doing this. 2, 2, 1. Okay. So S1 sends me here. S2 sends me here. So hopefully you see the pattern here. Here's S3, and here is S3. Okay. What's going to happen in the next level? Well, again, each one of these things has 2 arrows going down already, so the third one has to go up. So we get something like this, something like this, and something like this. And it's going to continue. Yeah. And the poset is exactly going to look like this. You have a layer of crosses, a layer of straight guys, a layer of crosses, a layer of straight guys, and so on. And this is what the root poset looks like for A2. And that means that we know exactly what the roots are. They're the things that are, they're basically the things where the numbers differ in 1, differ by 1 at most. Okay, the biggest difference between the coefficients is 1. And all of these things you can prove just by induction. Okay? I just wanted you to see what these root posets look like in the infinite case, and we're actually going to need to look at this more carefully in a second. So there's something that you should notice in that picture. Let me come back over here, which is that as we're going up this poset, the coefficients are increasing, and that's not entirely obvious. Yeah. For example, if I use S1, I know that it's the first coordinate that is going to change, but I don't necessarily know that it's becoming bigger. And so that's the next thing I'm going to show, is that really the coefficients are increasing as I go up. So proposition, if I have gamma larger than beta in the root poset, and if I write them in terms of the basis, let's say gamma is C1 alpha 1 up to Cn alpha n, and beta is B1 alpha 1 up to Bn alpha n. So in other words, the Ci's and the Bi's are exactly the numbers that I put in those little circles. Then each Ci is greater than the corresponding Bi. Okay. Now, the immediate question that you should be asking when you see this is the converse true? Does this characterize the root poset? Because if it does, then maybe this is a simpler definition than defining depth, etc. But you see that this doesn't characterize it, because you can see pairs that satisfy this condition, but not this one. For example, 1, 1, 0 is not less than 1, 2, 1 in the root poset. So this is not an if and only if. So not if and only if. So let's prove it. And of course, it's going to be enough to prove it for each edge. Okay. So it's enough prove it for each edge like this. So what's gamma? Well, gamma is SI beta. And SI beta is beta minus 2 times this expression. Right? So like I said, the only coefficient that changes is the alpha I coefficient. And so all I need to check is that this thing that I am adding here is positive. In other words, I have to prove that this thing is negative. Right? So that's what I'm going to prove. Okay. So let me make a couple of observations here. Gamma is equal to SI beta. And the depth of gamma is the depth of beta plus 1. Okay? Now, like I said, I can go back from roots to elements of the group. Each root corresponds to an element of the group. Gamma corresponds to the reflection T gamma. Right? Now, this is what does this correspond to? Well, we said that what it is you go here, then to this one, and then back to this one inverse. So this is SI T beta SI inverse, which is just SI. So this is this translated to the group. Okay? And remember that the length of gamma is basically half the length of this. Sorry, the depth of gamma is half the length of this. The depth of beta is basically half the length of this. And that means that the length of T gamma is 2 plus the length of T beta. So it is like it looks here. If I choose something reduced here, then this is the reduced word for T gamma. Okay? Why is that a good thing? Because then, let me make two observations. The first observation is that the length of SI T beta SI is bigger than the length of SI T beta. Right? But again, I want to keep going back and forth between the group and the roots. Here, I know how to translate this into root language, right? This is equivalent to saying that SI T beta takes alpha I into a positive root. It's equivalent. Okay. And let's also do it for the other one. The length of T beta SI is bigger than the length of T beta. And that means that T beta also takes alpha I into a positive root. Okay? So let me put these two things in boxes because I'm about to use them. Now, again, what I'm trying to prove is that this number right here is negative. Now, the reason that I like this is because this number is going to appear when I write out the expression for this thing. Let me show you that. What is T beta alpha I? Well, remember that this is a reflection, and it's a reflection for a reason, because it acts as a reflection geometrically. What it does is that it takes alpha I and it acts by reflection by beta. So it looks exactly like this. Yep. That's what T beta does to alpha I. And this right here is the number that I'm trying to figure out is negative. Okay. So I want to show that this is negative. And so let me just show it by contradiction. Let me first show it can't be 0, and then show that it can't be positive. Okay. Now, a thing that's important is that T beta alpha I is positive. And that's good news because that means that this is probably negative. This whole thing is positive. So again, let me take this thing, and first let's suppose that this thing is 0. And let's prove that it can't be. Why can it not be? Because then I would get that T beta alpha I leaves alpha I put. Actually, I had a different thing I was going to do, but I realized that I get a quicker contradiction because roots cannot be fixed by anything except for the identity. We proved this. So we proved that a root can only be fixed by the identity. And here I found something that fixes the root. If you don't remember that, let me show you the other thing I was going to do, which is then just apply Si on both sides. Si alpha I is negative alpha I. So this is a negative root, but over there I had said that it was positive. So I proved that something positive is negative.
For the part you said it can't be fixed by anything but the identity, we had roots like in the cube. We had roots that were on the plane that you wanted roots.
Oh yeah, it's a complete lie. Thank you. This is yeah. No. What we said is that what did we say? That the chambers.
You can't send it to its.
We said that the chambers of the reflection representation could not be fixed by a root. That's what we said. Not that the roots can't be fixed by a root. So I was about to make so that was a lie. It was a lie that roots cannot be fixed by a group element. Let me say that actually on the microphone so that people in Colombia can hear it also. In the example with the cube, you did have roots that were lined up with hyperplanes. And when you tried to reflect them, the hyperplane didn't do anything to the root. So this could be, and the reason it can't be is this. This is the proof that I had in mind. So this can't be. Contradiction. Okay. So now let's prove that it can't be negative. Sorry, that it can't be positive. What I want to prove is that it's negative. Okay. Now look at this expression. I have alpha I minus. This is a positive number. So I'm taking alpha I, subtracting something positive, and I'm staying positive. So if beta contained anything other than alpha I, then I would automatically get negative coefficients. So the only conceivable way that this could happen is if this looks like alpha I minus something times alpha I, where this something is small. Yeah? So the only way this could be is if beta is equal to alpha I. I mean, I get that beta is a multiple of alpha I, but I know that roots have unit length. Yeah. So if beta is a multiple of alpha I, then it has to be alpha I. Okay. And where's my contradiction now? My contradiction is in that the reflection corresponding to beta is T beta. The reflection corresponding to alpha I is Si. And supposedly Si alpha I is equal to alpha I. But we know that that's not true because Si alpha I is negative alpha I. So this is a contradiction. So that proves that beta and alpha I can't have a 0 or a positive inner product. That means that inner product is negative, which is what I wanted to show. And that proves my proposition. End of proof. So this proof just is good for kind of your mental piece. When you look at a picture like this, you really can think that each edge just means that you're adding something to one of the coefficients, and that something is positive. Okay. So now let me make a main definition that I want to make today, which is the definition of small roots.
Something you add be arbitrarily large, like from the first level to the second level we add 1 to some coordinate.
So in the first level we always add 1. Here we always had 2. Here we always had 1. Here we always had 2, etc.
So are there other root posets where you get 1, 3?
It's a good question for the forum. I mean, this is kind of what this is about, but I don't know the exact answer to your question, which is how. The question is basically how wild can these numbers be? Are they always like 1 and 2? They're not always this nice. The reason they're this nice is because the cosigns here happen to be -1/2. These numbers could be pretty ugly, but I think your question is also, are they small? Are they big? Can they be really big? And small roots is kind of what that's about. But a good question is, for example, can they be arbitrarily large? I think the answer is no, but I'm not sure. So small roots. Each edge looks like this. Here's gamma. Here's beta. The reflection is Si. And gamma looks like beta plus some positive thing times alpha I. Okay. This positive thing we know is -2 inner product of beta alpha I. Okay? And so I'm going to classify the edges as short or long. And the threshold is 2. So if C is 2 or bigger, then I call this a long edge. And if C is smaller than 2, then I call this a short edge. So if C is bigger than 2, long edge. And if C is less than or equal to 2, then short edge. Okay. So, like we already said here, these edges are all 1s. You increase by 1 each time. Here you increase by 2 each time. Here by 1, here by 2. And so here we have short, long, etc. Okay. Sorry. The equality goes the other way. So if you have a 2, you're long. And that's yeah. And so what I'm going to do now is I'm going to just kind of break the long edges here. So let me just make them dotted. Okay. So they're still there, but they're long. Okay. But these are the short ones, long ones, short ones, long ones. Now, what's a short root? A short root is one that you can reach from the bottom level, walking up, and only using short edges. In other words, that's why I said that I wanted to break the long edges. They're too long and you get tired, you don't want to walk across a long edge. You can only handle short edges. Okay? So you start at the bottom and then you walk up as much as you can, but if you get to a long edge, you're stuck. Okay? And the short roots are exactly the ones that you can get to. Definition, a short root. This is a little box. Definition. small root is one reachable from the bottom of the root poset by going up short edges only. Okay. So that's a small root. Now, I hope the first thing you're asking yourself is why on earth would I ever want to define this? It seems like the most arbitrary definition on the planet. Why do I classify these between small and short? Why did I choose 2 here and not some other number? But my understanding is that this is really historically how this happened, is people really figured out that that was the sharp threshold that you cared about. And I'm going to justify to you why this is a good definition by giving you another characterization of small roots that, that is quite natural. Okay. So what are the short roots in this picture? Well, basically, it's the first 2 levels. Okay. So these right here are my short roots. Now, I'll ask you to go back to your picture of S4 and tell me what the short roots were there.
Short and smaller synonymous here.
Sorry, small. I shouldn't say short. Small. So there, if you look at it, first you had 0, 0, 1, etc. And then if you look at it, all the numbers were 1. Yeah? It was either 0, 0, 1 or 0, 1, 1 or 1, 1, 1. So if you only have 1s, that means you can never increase by 2 or more. So that means that everything is short. So in S3, all roots are small. In S4. Well, in S3 it's also true. In A2, the small roots are alpha 1, alpha 2, alpha 3, alpha 1 plus alpha 2, alpha 1 plus alpha 3, and alpha 2 plus alpha 3. So, let's talk about a different characterization of small roots. Let's put it in here. Another characterization. So here's a little parenthesis. What does it mean for u to be less than v in the left weak order? Well, there were different ways of saying this, but one way of saying this was that the descent set of u was contained in the descent set of v. What's the descent set? The descent set is the reflections that you multiply by, and they make you smaller. But now we can translate that into root language. And that means that those are the roots that were positive, and you make them negative. Okay? So what is this saying? This is saying u is less than v in the left weak order when for alpha bigger than 0. If u sends it to a positive root, no, negative root. I'm a little worried. I might get it backwards here, but I think this is right. So one characterization of the left weak order is u is less than v if the roots that u makes negative, v also makes negative. Okay? Now, we could make exactly the same definition but turning it around. And now think about the situation not by comparing two elements of the group, but by comparing two roots. Okay? And so we could say that a root alpha is bigger than a root beta. Actually, let me call them beta and gamma so that you don't confuse them with the simple roots. Leave a little space here. If and only if the same thing happens but the other way around. If w sends alpha to a negative root, then beta, all the elements that send beta to negative also send gamma to negative. So for beta and gamma positive, I'm going to say that beta dominates gamma when this condition holds. So it's the analogous condition, just switching it around and thinking that now I want to see how this happens with roots. Okay? Positive roots. Now, first of all, is this a poset on the roots? The domination poset. Does that such a thing exist? Well, the main property that you would have to check is transitivity. If beta dominates gamma and gamma dominates delta, is it true that beta dominates delta? And you see clearly that that's true. So this is a poset. The next natural question to ask is it the same poset? Is it the root poset? And the answer turns out to be no, this is not the root poset. Okay? But it's related to the root poset. And it's related in the following way. I mean, I hope you agree that this is a natural poset structure to define. It's basically the analogous of the left weak order. Okay? And the theorem is that a positive root is small if and only if it doesn't dominate anybody. Okay. In other words, the small roots are exactly the minimal elements in the domination poset. And if I define them to you in this way, then I think you'll agree that they're a natural object. If I define them to you in this way, there's no reason why you should believe me that these are an interesting object to study. Okay. And so the next thing I want to do is sketch a proof of this theorem. So this theorem relies on a little technical lemma that says this. It says that it basically tells you when a root dominates a simple root. Turns out that you can describe this in a very simple way. Beta dominates alpha I if and only if their inner product is greater than or equal to 1. So that means that it's pretty easy to describe when some root dominates a simple root. So this is my first lemma, and I'm going to ask you to see how to do this in the book. Huh? You look worried. It's okay. And I'm going to show you how, using this lemma, we can prove this theorem. So let me prove another lemma, which is the following. If you have some relation like this, and here you have a long edge, then gamma dominates someone. Some other root. And if gamma and beta are joined by a short edge, then gamma dominates someone if and only if beta dominates someone. Okay. So that means that domination is kind of inherited along these short edges. So let's prove this lemma. For the first thing, let's suppose that it looks like this. So then gamma is equal to S beta for a long thing, okay? Which means that it's beta plus something greater than or equal to 2 times alpha I. And this number right here is minus 2 like this, okay? So that means that the inner product of beta and alpha I is what? It's less than or equal to -1. Yeah? Now, if I just kind of reverse this, I'm going to find that gamma alpha I is just the negative of this. Do you believe that? This is an easy exercise. You should do it. This is easy. Think about it and you'll see it. And then what I just proved is that gamma dominates alpha I. By this lemma. Now, part B. Let's suppose that gamma is equal to S beta, and it's a short edge. So this is beta plus something less than 2 times alpha I. So what that means is that the inner product of beta and alpha I is now, it's not bigger than -1. It's not less than -1. It's bigger than -1, but it is negative. Actually, it's strictly negative. Okay? It can't be 0 because we're really going up or down the poset. Okay? And so, okay. So now, suppose that beta dominates something. Let's say delta. Okay. Then I know that delta cannot be alpha I, right? Because if beta dominated alpha I, then this number would be in this range, not in this range. Okay. So if beta dominates something, that something cannot be alpha I. Okay. And so that means that if delta is not alpha I, then when I do Si alpha I, I'm going to get something positive. Because the only positive root that Si makes negative is alpha I itself. Okay. Si alpha I is positive. Okay. What happened? Si delta, I'm sorry. Delta is not alpha I. And alpha I is the only thing that I could put here to get a negative thing. Si delta is positive. Now, I want you to think about this. What happens if I claim that this is equivalent to saying Si beta dominates Si delta. Because if you look at this definition, if you stick an Si in front of here and an Si in front of here, then all you're doing is that instead of W, you have WSI. But if W is ranging over the whole group, that means that WSI is also ranging over the whole group. So if beta dominates gamma, then also Si beta is going to dominate Si gamma. Here beta dominates delta, so Si beta is going to dominate Si delta, which, by the way, is positive. It's important. But Si beta is gamma. So I started with beta dominating something, and I ended up with gamma dominating something. And the reverse argument is exactly the same. Okay. So that proves this lemma. Okay. And now I can prove the theorem for you easily. Proof of this theorem. So let me take a small root and let me show that it dominates nobody. Okay. Take beta small. I need to show that it dominates nobody. Well, what I do then is that because beta is small, that means that I can get from the bottom to beta using only short edges. Short, 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 short. Okay. So beta dominates someone if and only if this guy dominates someone, if and only if this guy dominates someone, etc. If and only if the simple root alpha I dominates someone. Okay. Beta dominates someone if and only if alpha I dominates someone. Now, can a simple root dominate someone? No, because simple roots are the ones for which this happens most often. Least often, sorry. Yeah. If beta is a simple root, did I write this backwards? I think I'm just getting a... The point is that this is clear because the only root, the only group element that sends alpha to a negative root is Si. I might have something backwards there, but this is just doesn't even require a proof. So this doesn't happen. That means that this doesn't happen. And if beta is long, well, rather, if that beta dominates no one, take a path from beta to a simple root, and if at any point in this path I have a long root, I have a long edge, that would mean that the top thing there would dominate someone, and that would mean that beta dominates someone. Okay. So if here I have a long edge, the first long edge, then here I said that beta dominates someone, sorry, dominates no one. That means that this guy dominates no one either, because these are all short. And that contradicts that anything on top of a long edge dominates someone, by my lemma. Okay. And so that completes the proof of this statement. All right. So that's a good place to stop. Next time I'll show you how to use these small roots to prove what we want to prove.